So the reading, writing, solutions journals, and some kind of random topics. Journal number 1 is now, I think, entirely graded. Anybody that had stuff posted should be graded, because I've been grading that since roughly 3 a.m. till about 11 today. Intermittently, it didn't take me that long to read them all. But so those are mostly graded. Some of them have comments, kind of little bits and feedback. I've summarized some of the comments here for a second. Journal number 2 is also now entirely officially graded as well. I hope to be completely caught up with your Thursday journals, which is the solutions chemistry aspect, by next meeting. Feel free to yell at me if I haven't. Okay. One of the big things that I noticed, there's the English portion and the chemistry portion, and people were uploading separate files. It's not that that's necessarily wrong, but me as a new Canvas user went through, and in a couple cases you might see a comment saying, "What, you didn't do the English class part, you're not going to get full credit," and then you have full credit. Why is that? Okay, that's because when I graded it, I noticed I didn't find the English part, so I commented that's what was going on, and then I found out later that if I scroll down, I could find the English part. Okay? So ideally, when you do your upload, it's a single document, okay, so that we aren't sorting through it, and it's ideally done at the same instant for both the English and the chemistry. I'm at least aware now to be looking through multiple iterations or multiple posts, so I will be watching for that, but if it looks like you're not getting credit and the comment is saying you didn't do it all, feel free to comment back and say, "Yeah, I did. Try scrolling down." Okay. You could even add the term "idiot" afterwards, but ideally you kind of avoid that. Yeah.
What about text? Like, you can post as text?
You can post, so there's a variety of file formats, which is the next thing coming up here. You can post as just raw text. That's fine. Uploading actual documents, Canvas seems to read some of them and not read others, so that when I have to click it and it opens up in a separate window. I don't have any problems either way. The text is easier because I don't have to do any extra step, but it's fine either way.
The problems you give us that we solve and then describe how I solve them in
Yes.
50 to 100 words, that's starting this Thursday?
That is starting next week, Thursday.
Okay.
So I will have, because we don't have questions available yet. So that is on my to-do to be done by the end of Friday.
Thank you.
Okay. So that you have the weekend to potentially work on that.
I got the chem journals that we do with the comparison that we work into it, and use that when we're talking about it.
For those,
keep an eye on the assignment journal details from those to be updated. Keep going back to that Google Doc folder file.
yeah. So look at those journal details because that's where that information is going to be found. Okay. For those of you that use Macs, Pages, you should stop using it. There's definitely better software out there, but if you're using it, that's fine. At least save it as a different file format. I personally can open it. Greg, not having a Mac, is going to have a really hard time opening that document and can't give you credit for it if you upload it as a Pages document.
And Canvas doesn't read it.
Okay, and Canvas absolutely won't read it, yeah. Yes,
Is rich text format all right?
that should be fine.
Or you can export as a Word document.
And yeah, and if you're in Pages, you should be able to export as a variety of different formats, and I don't remember them all, but I would guess they've got at least the PDF option. What's that? They do Word now too? Yeah. This was saying at least on the chem side, but it actually applies to both. These are just my quick notes. A few people provided lists of keywords. Keywords are important to recognize, particularly within chemistry. We've got a lot of vocabulary coming in, and a lot of that is new. So it is helpful to provide a list of keywords, but that's not the point of the writing assignment. Okay? You need to be writing sentences. So at very least, define those keywords, and you've now kind of completed that part of the assignment. Okay? If for any reason something kind of scales off, at least from the chem side and probably from the English side as well, we will comment and let you know, hey, this is what you're missing, you need to fix this.
Most of you guys are doing, honestly, a really great job with the reading journals. Just a few of you guys are like kind of just doing that bullet point sentences and instead of creating this cohesive paragraph of summary. And a few of you did the keyword thing.
I also found it because a couple people went through and did this, brought in their own personal experiences. So they read the text and were like, actually, this part of the text reminded me of something that I did in my own life or something I'm working on. That's cool. Okay? Tying the chemistry concepts to something outside of the chemistry or English class will help you remember those concepts. It's a good thing to go ahead and include if you've got it. If you don't have little anecdotes, don't worry about it. Okay? But that is a good thing to include as far as I'm concerned. And I know I was supposed to get this up earlier, but it is finally up. The Science Center worksheet form is up. It is available. The same place that you get the English Center form. The Science Center form is now linked there. You should click that. Same idea as the English or the Writing Center. You'll print that out. You complete some parts of it. You take that into the Science Center and work with the tutors, get it signed off, and then upload that back, and we'll go through and grade that. Okay?
So you
Question?
upload a picture or scanned a copy of your tutoring sheet, visit sheet, and you hang on to the visit sheet for your own record to help you study for a chemistry exam or to hang on to the feedback and apply it to the next writing you have.
Yeah. So you got a lot of feedback with help in solving those questions. We don't want to take that help away from you. Okay, that's why you should be uploading a digital image of it, and you can keep the hard copies. Make sense? Okay. So we were looking at our line spectrum when it came to light. And if we look at each individual element, what ends up happening is that when we trap it and pump 20,000 volts into them, they end up emitting light. And they emit light in distinct bands, not a continuous spectrum. The conclusion that came from this was what? The electrons can only exist at different energy levels, okay? Or orbitals. It's a fair term. And so when we're looking at that light emission, it's an electron jumping from one orbital step to a different orbital step. It can't do half jumps. Okay? So we're looking at kind of a stair-step process. We can only exist on the levels of the step. So when we change aspects of the element, like the number of protons or the number of electrons, that changes all of those energy levels, which then means we get different outputs, okay, after we pump in the voltage. Okay? So our big conclusion from all of those pretty kind of images is that we have atomic orbitals. Okay? So if we then try and look at our homes, we don't want to use a fancy word, we can start at our lowest energy level, and our lowest energy level should be located where? Okay, as close as possible to the nucleus. Okay, why?
It takes energy to sit down.
It's not so much that it's taking energy to sit down. Our electrons are high energy particles. Okay, that's how we use electricity, is that it's high energy. If it wasn't high energy, we wouldn't be using it, okay, because it wouldn't give us anything. So electrons are inherently high in energy. Okay? What do our high energy particles want to do?
Fly.
Become low energy. It's as simple as that. Everything is striving for the lowest energy possible. How do I make a negatively charged particle lower in energy? Neutralize it. Okay? Where do I have something that can cancel a negative charge? The protons, which are found in the nucleus. So I will place my electrons at the lowest energy level, which is closest to the nucleus. Okay? As I raise the energy, okay, add more energy into that electron, eventually what happens?
It wants to shoot back down. It's going to hit us.
It's
It's going to hit a beat.
It's-
and then it's going to go down.
So we talked about, it's not a ceiling per se. What happens?
It peaks.
Oh, does it get ripped away?
It's no longer part of the atom. If it's no longer part of the atom, is it in an orbital? No, because the orbital is the electron home associated with the atom. So we have kind of a maximum energy level. It's not really a ceiling because we can continue to raise that energy, but now that electron is no longer associated with the atom. Okay, so you will sometimes see people reference the highest energy level possible as being oops, I think I spelled that right, in vacuo, meaning in the vacuum. Okay? It's not associated with anything. There's nothing else present. That's what a vacuum is. There's nothing present. Okay? So the next part is then how do we then fill in our energy levels? Well, according to our Bohr model and what we're seeing with our atomic line spectrum is that we know that there have to be individual steps somehow following through this. Okay? And as you notice here, I drew them roughly all kind of equal. Okay? Well, based off of the atomic line spectrum and some fancy physics and calculations, we actually found out they aren't equally spaced. The further I get away from the nucleus, okay, the tighter the energy levels become. Okay? And that has to do with how the electrons are being held by the nucleus. As I get further and further away, remember I'm at a cap. If I go beyond that cap, I'm in the vacuum. So eventually those energy levels are going to have to kind of stack up on top of each other. And when we looked at this, we end up with 7 energy levels. Okay? How many electrons did we predict to be able to put in an individual orbital? 2. Okay, why do we say 2? It's a weird one.
They have to be, or they push each other away.
Electrons push each other away. Okay? Like charges repel. Okay? So why do we even get 2? Because don't I bring a negative near a negative? Shouldn't they repel away?
Because the positive in the middle of the nucleus.
There's actually nothing to do with the nucleus. It has to do with the individual electrons. They spin different directions. Okay? Which is stupidly confusing, but that is the quantum mechanical explanation of what's happening. Our electrons spin different directions, and because they're spinning different directions, they don't see each other's charge. But I only have 2 directions I can spin, left or right. If I try to put a third particle in there, it's either going to spin left or right, which then means it matches one of the other 2 that are already there, and it gets ejected. Okay? So if we tried to place electrons into this, we could go through and say, well, each of those energy levels has 2 electrons, and we would end up with a total of how many electrons? And notice the spin I'm representing by the arrow, either up or down. I would end up with 14, which would say how many elements can I get? 14. That matched the periodic table. How many boxes are on the periodic table? 118. Does that match 14? No. Okay. So something about this model is incorrect. We're missing a piece. Okay. And as we kind of dug into this, what we started to notice was that these energy levels can split, and they can break into other types of orbitals. Yes?
I was going to say that there can also be multiple layers of energy levels too.
That's kind of getting at what we're looking at here. Okay, so first and foremost, we have our energy level, okay, with seven energy levels. Why the pause? Anybody actually follow what my face was doing?
You're counting
What was I counting?
the rows and
The rows on the periodic table. If you look at the rows on the periodic table, how many rows are there? How many energy levels do we have? 7. Theoretically, we could keep going, and we could get 8, 9, and 10, but remember, those are now going to become increasingly tighter up against the vacuum, meaning that very quickly the electron is going to jump into the vacuum. Okay. Everybody counted 7 rows? Really? Nobody counted 9 rows? Okay, I didn't know if you heard about this or not. So remember, these bottom 2 rows are actually folded in to the main one. So we really only have 7 rows. These have just been separated out. Why did we separate them out?
Because otherwise the periodic table would be...
It gets too big. Why do we have paragraphs? It looks pretty. Why do we have a second section of this table separated out of it? It looks pretty. Okay, that's it. Okay, paragraphs actually have a little bit more importance than just looking pretty. Okay, but it's the same concept. Okay, so we've got these 7 energy levels. I'm trying. Okay, But that doesn't account for all of our elements. So what they ended up noticing is that with each energy level I increase the possible types of orbitals that can occupy that space or that energy level. Okay? So as I go up, let's not look at that. The first energy level, how many types can I have? I have one type. Each type can hold 2 electrons. When I move up to the second energy level, I now have an extra type of orbital. Okay? When I move up to the third energy level, I now have an extra type of orbital. If I had one type here, how many types did I have at the second?
2,
How many types did I have at the third?
3,
How many types did I have at the seventh? 7, just testing. Okay? So what we end up doing is now increasing the possibilities. That energy level divides out into multiple different types. Okay? That gets me more electrons. Anybody really good at math and can propagate that all out to see how many electrons we could possibly put in there? No one's really good at math?
2, 3, 5.
Okay. I'm not really good at it either. Guess what? Doesn't equal 118. Okay? So our model is still wrong. Okay? We're still missing something. Okay? Well, what that something is now has to do with the orbital orientation. Okay? So what we've got is different layers of information. Our energy level, okay, tells us the row that we're looking at. The orbital type we'll actually find in our columns, which we'll talk about. And the orbital orientation is really just a way of telling us how many of that type we have. Okay? Well, to figure out an orientation, what do we need to know something about?
starting point.
What our starting thing looks like. What does our orbital look like? Our lowest energy has only one orbital available to it. What is that orbital? What does it look like, maybe? Round. I'll accept that. Okay. I'll accept a circle even better.
An S.
But I'm going to argue it's not a circle. It's
Here.
a sphere because we're dealing in 3 dimensions. Sphere begins with S. What should we call this orbital that is a circle? The S orbital. Oh, look at that. Creative. Okay. Don't assume that's going to work all the time, because it doesn't. Okay. But it's close enough for what we need to deal with. Okay. What happens when we move up to the second energy level? Okay. We add another type. So we have what for our first one? It's still the sphere. I'm copying the previous orbitals, but I'm now at a different energy level. So I will still end up with the sphere type. Okay? Or the S orbital. What's the one extra one? Okay, we can go with shapes, or we can go with names. P is the name of it, the shape.
Parabola? No.
2 teardrops.
It's getting 2 teardrops, I'll accept that. Okay. When it comes to naming the shapes, you might say, well, it's kind of arbitrary, right? A lot of things are arbitrary, except in science we have to come up with an accepted definition. The name of the p orbital shape is dumbbell. Sorry, that's what you got to deal with. Don't shoot the messenger. It's called a dumbbell. That's what you got to deal with. Okay. The reason we wanted to look at these shapes, though, came back to this orientation. If I take that sphere, how many possible orientations are there for the sphere? I take a sphere and I rotate it. Can you tell that it rotated? No. Okay. Nothing about it tells that you can rotate it. There's no lobes or dinguses to help you mark that rotation, which means there is one orientation. How many orbitals do I get for an S type? 1. which means I can only fit 2 electrons into the s orbital. What happens when I move up to this one? The exact same thing. There's still only one orientation. It's still a sphere. How is that sphere different from the bottom one?
It's larger and encompasses the.
How do you know it's larger?
Well, it's gotta fit around there.
Okay, we can think about sizing it. It has to fit around the previous one.
As well as the electrons are repelling each other.
The electrons are higher in energy, which then meant they were further from the nucleus, which then means it naturally has to be bigger. Okay? What happens when we move to the p orbital? Or our dumbbell? Can you tell when that orbital is rotated? Yes. Okay. We can tell that it has been rotated if it looks like that. Okay. Remember, we're in 3 dimensions. Instead of it being vertical or sideways, it could be directly at you, which is really awesome to draw. For those of you that are artists, maybe you can help out with this. Trying to do a little perspective there. One's going away. If we looked at it directly end on, all we'd see is that. It's not really helpful. So we could say we've got the other lobe in behind it. Where are these orbitals aligned? I know that's a weird statement. Math class. What was that? On the different axes, x, y, and z. So we could further label those now orbital orientations as the px, the py, and the pz. Do we need that extra information? No. Okay, we'll just refer to them as 3 different orientations. Each of these orientations represents a distinct orbital, which then means how many electrons can I fit in the pz orientation? 2. How many electrons can I fit in the py? How many electrons can I fit in all of the p orbitals? 6, because there's 3 orientations. And you might say, well, that's a crap load of information to have to memorize. But no. Why do we not have to memorize that?
It's already on the periodic table.
Already on the periodic table. It's given to you on the periodic table. Okay. The rows were the energy level. Okay. The columns are the orbital type, and they get us information about the number of electrons in that orbital type. Okay. And this is where I don't have a periodic table. I meant to put it on my computer. So let's start with hydrogen. How many electrons does hydrogen have? Hydrogen has 1 electron. Where should that first electron go? The first energy level. Have we named the first energy level yet? S was the type. What's the energy level? First is 1. Super creative. So if I want to reference where that single electron on our hydrogen atom is located, it's located in the first energy level, so I can say it's 1. What orbital? The s orbital. Okay. So it is in the 1s orbital. How many electrons does hydrogen contribute? It is 1s1. What I've now just done is the electron configuration for the element hydrogen. It is 1s1. What happens if I make this more difficult? Helium has how many electrons?
2.
2. Tell me where those 2 electrons are located. Where's the first electron? First energy level. So 1. What type of orbital is it? S. So there's the first electron. It's located in the 1s orbital. Where's the second electron? It's still the first energy level, because remember, our first energy level can fit 2 electrons. Okay? It would become 1s, first energy level, s type, and I can fit another electron there. That's going to get a bit redundant. Couldn't we condense that? 1s2. Yes? This is your electron configuration. Okay, and for those of you on that side, sorry, I'll stop using blue. Because it doesn't really show up very well. So we have our 1s2 for our electron configuration. Okay. Where's hydrogen? On the periodic table. Top left, in the first row. I know, that was a vague question, but you guys got it. First row. How many columns are in the first row? Let me rephrase that. Hold on. How many columns are occupied by elements in the first row? 2. How many electrons could we fit into the first energy level? 2. It was 1s2. Scale this up. What happens if we now move to helium? Sorry, I just did helium. The next one. Let's be more difficult. Let's do beryllium. How many electrons does beryllium have?
4.
Where does the first electron go?
LS1.
The first energy level, the S type, that would be 1s1, referencing that 1 electron. Where's the next electron go? Same place. Where's the next electron go? It has to move up to the second energy level, okay? Because there's no more space in the first energy level. So we move up to the 2. What is the lowest orbital type energy within the second energy level? Rs. So it becomes 2s1. Where's the fourth electron go? 2s1. Again, really stupidly redundant to draw all that out. So what do we end up drawing? 1s2, 2s2. Okay. Where was hydrogen found? Let's try that again. Let's look at that second energy level. Okay, for beryllium. Which column was it located in? The second column. And the second row. Okay. Where is it grouped with? Hydrogen, closer to hydrogen and closer to helium. That's not going to work. How do I want to describe that? It is located in those first 2 columns if we separate out our periodic table, right? Beryllium and lithium are kind of grouped with each other. So in that first column, we've got lithium and beryllium grouped next to each other, and then some way somewhere else, I've got a bunch of other things grouped next to each other. Okay. What was the electron configuration for lithium? 1s2, 2s1. What was the difference between them? 1 less electron. The electron configuration, though, as far as the orbital types,
So just on the same energy level?
was the same.
Yeah.
This first 2 columns are referred to as the, someone said it, the s orbitals. Why? When we look at the outermost electrons for any element in those first 2 columns, what orbital are we going to be looking at? The s. Okay. Our second energy level, though, what happens as we scale this up and add, say, another electron? We move to now boron. How many electrons does boron have? 5. So we'd still have our 1s1, our 1s1, our 2s1, our 2s1, 1s2, 2s2. The next electron.
2p.
2, because I'm still in that second energy level. Remember, the second energy level split into another type. What's that other type? It was our p type. How many electrons are in that p type for boron? 1 more, 2p1. If we add our subscripts, what do we get? Fair enough, 5. Don't tell me 5. What else do we get? The number of electrons for whatever electron configuration we're looking at. Make sense? Okay. how many electrons could we fit in the p orbitals? So remember, we had how many orientations for the p orbitals? 3 orientations. And I said we didn't really have to memorize this. Okay, why not? Well, if I had 3 possible orientations, and each of those orientations can hold how many electrons? 2. The p orbitals have a grand total of how many electrons? 6. In that second energy level, we went from lithium to beryllium, which we said were part of the s block, and then there was a whole nother section. I don't know why that was an appropriate sound, but it works. We get to boron and another set. Okay? Boron is now part of another group. How many other elements are part of boron's group in that row? Total of 6. Wait, how many electrons in the p orbitals? 6. That is because when we look at boron through neon, anything under boron and neon, their outermost electrons are going to fill which orbital? The p orbital. They're known as the p block. What happens as we continue to add up? Let's jump to now, let's come up with a more difficult one. Are we ready for a more difficult one?
Plutonium.
I'm not doing plutonium. Let's jump to S. Yeah, let's do sulfur. Okay, and by let's, I'm going to flip that. You do sulfur. Give me the electron configuration for sulfur. Talk to the people around you. Do your own work. Come up with the electron configuration for sulfur.
So each level so for each, that's what I'm trying to get. So like for each row.
So with sulfur, very first thing we have to do is find what? Before even naming the orbitals, the very first thing we have to do when we try and determine our electron configurations. Atomic number, because what are we looking for? We're looking for our number of electrons. So sulfur in its neutral state has 16 electrons. Right? Yeah. Okay, sorry. First electron needs to go where? Lowest energy level, which is our first energy level. Okay. So we could even look at our periodic table to help us out. Our first energy level is the highest one up there. So that's our 1. Okay. The type. Okay. And our first energy level messes with us a little bit. What's our type for our first energy level? S. How many electrons fit in the first energy level? Count the columns in the first row. There's 2. How many electrons can I put there? 2. Okay. That accounts for 2 electrons. Sulfur needs how many? 16. Am I done? No, I still have to start counting for the next electron and the next electron. The next electron cannot go into the first energy level because it's full. There's no other locations. So we will then have to move to the second energy level. What is the first orbital that I will fill for the second energy level? The S type. How many electrons can fit into the S type orbital? 2. Am I done now? No. Why not? That totals to 4 and I need 16. So I need to put in another orbital. Does the second energy level, does the second row have another bank of elements?
Yes.
Yes, which means another, yes,
More room for like
another orbital type. So we're now at our second energy level. We have a new orbital type. What do we want to name that orbital type? We will name it P. Why P? I have no freaking clue. Because dumbbell in German begins with P. Anybody speak German? Don't check it, because I'm probably wrong. Okay. P was established because that was the physical constant or physical variable used when they solved the calculations. Okay. Where's the next electron go? It's still going to go into the p orbital. Why did you say 2p6?
Because it's going to fill it all up.
There are 6 columns to get through the second energy level. Okay, or that p. So, dumbbell in Latin begins with p.
okay, I can check that too.
Okay. Why do we have to fill the full second energy level?
Because it's to make sulfur.
we're not there yet. How many electrons have we accounted for so far? 10, and we need 16. So we aren't there. We can completely fill the 2p energy level, or the 2p orbitals. That's why we'll write 6. Okay? What's our next available orbital? Well, when we look at that second row, are there any more blocks, any more places that I can put stuff? Nope, which then means I have to move to the next energy level, which then becomes 3. The first orbital available to me in that third energy level is the S type. How many electrons can I fit into the S type? 2. Should I be putting 2 electrons in the S type? Why? I need to fill it up because this totals not to 16. What's the next orbital I encounter? Still the third energy level, and as I move through that third energy level, I move into that next block, just like we did with the boron. It's a new group. That was our P block. That's our 3P. Why'd you say 4? We only need 16 electrons. I know the p orbitals can hold up to 6 electrons. I only need 4 to get to sulfur. What have I now done? The electron configuration for sulfur. Okay. Take a second to process that. Okay, because the next one. So what happens when you go beyond row 3? Okay. What happens when we move to the third energy level? We add our 3s, our 3p, and our 3d. Okay. So let's fill the 3p. If we filled the 3p orbital, what element would we have? We're following along nicely. I like it. So we'd be at argon. So here's for the Mindbender. What orbital would you expect to put the next electron in?
Initially for 4s.
No,
Why 3d?
because that's the next layer. That's the next
Okay.
orientation.
Remember how our orbitals went. We had our lowest energy level. There's our 1s. There's our 2s. There's our 2p. We move up to the next one. We had our 3s, our 3p, and we have a new orbital type. What's that new orbital type called? It's called our d orbital because we're at the third energy level. We'll call it our 3d. If I've filled 3p, what should be the next orbital that I would predict to fill? 3d. Why do you say the 3d? Because 3 is a smaller number than 4. And when we filled our orbitals, how did we fill? Lowest energy, not necessarily in order. So we would predict for the very next element, what's the very next element after argon? With 19 electrons, we would expect, at least the way this is being described, 1s2, 2p6. Oh, come on, 3p6. And we would say then 3d1.
In argon, oh wait,
Do we have the electrons accounted for here?
Yes.
Don't we? 10? Yeah, we've got 19 electrons in this. Okay, that's a 2. It's a 2, not a 7. Knock it off. Okay. Where is potassium located on our periodic table?
On the row 1.
Row 1. What did we say lithium was the leader of? The S block. Where is potassium? In the S block. What should be the orbital filled for potassium? The S orbital. Which S orbital? The fourth, because fourth row. That's what our rows tell us, is our energy levels. Right? So when we look at the actual electron configuration for potassium, it is not 3d1, it is 4s1. Okay? So why did the 3d not fill yet? Okay. There's all sorts of fun explanations for it. The answer that I'm hearing from you guys is because potassium's not in the S block, or not in the D block. So really what you're saying is that the periodic table has this inherent organization behind it. We're going to follow the inherent organization. We don't really care of anything else. Cool. That's perfectly valid. Okay. Why does the 4s fill first? It's a lovely answer. Symmetry. The molecule is more symmetric with one s orbital half filled than one of 5 possible d orbitals half filled. All right, so well, why do we care about symmetry? Well, let's take a moment. We can all close our eyes. And since my eyes are going to be open, you can close them, and I can see that. And you can think of the most beautiful person or handsome person on the planet. And stop looking at me. That's why you had to close your eyes. I don't want to be a part of this. Okay? And imagine a line drawn through the middle of their face. What you will find is with people that have been considered beautiful, they are symmetric across the faces of their half. Or halves of their faces. One of those two phrases. Symmetry is inherently beautiful. You can open your eyes now if you wanted. Okay? Atomic structure follows symmetry. Reactions follow symmetry. Okay? We fill the 4s because we get a better symmetrical structure than by filling the 3d first. Okay? Then what happens? Okay, let's move beyond potassium to magnesium. Magnesium has how many electrons? Where am I? Not magnesium. What's after potassium? Calcium. Those are close enough, right? You could laugh at that. That's okay. 20 electrons. Where's that next electron go? I still have an open slot in the s orbital. I get 4s2. Okay? Not only do I still have an open slot, where is calcium located? In the first 2 columns, known as the s block. Next element is scandium. Those of you that have been working on your naming of your elements, good job. Those of you that didn't get it, you should start working on that. Where does that next electron go? Is it in the s block? Is it in the p block? So what does that mean? New orbital, it's got to be a d orbital. Where is that d orbital as far as the energy level goes? It goes back 1. Okay? Why do we go back 1? Because of the fill pattern on what we set up. And we might panic and say, well, how could we possibly memorize that? Again, you don't have to memorize it because it's already on the periodic table. The only thing that's missing is that 3D. You just have to memorize the d orbitals are offset 1, 3. What happens when you get to lanthanum? Lanthanum? La, let's stick with that. That should I was about to draw on my screen. That doesn't work. That should insert where? Here, right? Which should be in what type of orbital? Okay. But if it was D, shouldn't it belong in this? Is it actually shown in that? Shown as a whole separate section. Why is it shown as a whole separate section? It's a whole new orbital type. Okay. That orbital type is known as the F block. Okay. F for, why would you put that there? Okay. Failure to fit in. That works. Okay. That first energy level for our F block will be which? 1, 2, 3, 4, 5, 6, 7. Okay. Why are we saying 5? 1, 2, 3, 4, 5. We went back 1 because of the d orbitals. But what are the f orbitals doing? Same thing that the d orbitals are. You have to go back 1 for them as well. Which means that very first one is the 4f. Okay? For those of you going, oh my God, how can I ever have to deal with that? Okay, you notice an interesting feature on most of or a significant chunk of the elements in the F block. They're all with that little white outline, right? What does that mean? They're man-made, which means what are their abundance in the world? Very, very, very tiny. For some of the other elements on there, what might you notice? Uranium? What can you tell me about uranium?
It's very, very.
Small concentrations, okay, yeah, really. So we got uranium out in the parking lot. We just go out and shovel it up. Hey, yeah, let's sell some uranium. Why is it expensive?
There's not a lot of it.
There's not a lot of it, and
Dangerous to handle.
why is it dangerous to handle? It's radioactive. Guess what most of the F block elements have to deal with? Radioactivity. What are the odds you are ever going to encounter a radioactive element in this class? Slim to none. And guess what that means? Don't effing worry about it. Right? 151, because you have to recognize where the patterns are coming from. The patterns are still there. 151, you may be asked, depending on your instructor, to do information like that, to look at those electron configurations if you have to take more chem. If you don't, then don't worry about it. We are going to be primarily focused up to that third energy level, which means we will include the d orbitals as kind of a last-minute check for that first row of the d orbitals when looking at electron configurations. Okay? But for the most part, we will keep everything in the first two energy levels. Why? Because I'm an organic chemist, and organic chemists see way too many numbers on the periodic table, and we eliminate all but 10 elements to work with. Those 10 elements all happen to be in either the S or the P block because their electron configurations are stupidly easy to work with. You can follow right off the periodic table. We don't have to deal with weird patterns in d orbitals or f orbitals, any of that nonsense. Okay? So we will keep our focus in on the easier elements, and those first three, or we'll say first 4 rows. You should be able to come up with the electron configurations for every single one of those. Believe it or not, those answers, give me a sec. Those answers for the electron configurations are readily available. Okay, so what can you do to practice? You have the answers. All you got to do is write the electron configuration and compare. Did you get the right answer? Yes? You know what you're doing. You can do it for all 36 elements. If you can do it for all 36, you will be ready for any question I'll throw at you. Yes?
I don't know if you already said this, but like 3D10,
Mm-hmm.
go to 4P1.
So what happens when we fill zinc? Okay, the very next electron goes to gallium, which is located in the P block. What energy level are we now looking at? It's the 4th energy level because it's the 4th row. Your S and P blocks match perfectly with the energy levels. Your D and F are offset. Everything else follows. The periodic table gives you that information. You just have to recognize those patterns.
So would you want us to write it as 3P6, 3D1?
It gets written as 4S2, 3D1, or 3D blank. We can imply that one. Okay. That's an awful lot of writing, particularly if we jumped, say, to bromine. Okay. So if I had you fill in the electron configuration for bromine, you might have a tedious time of going through and doing that. I wish there was a shorthand that we could do.
And then just as a, and then with the F layer, where would that go? Because I'm just correcting one.
So as you fill through, when you first get to the F, that's where it goes. So the F is first going to show up after you fill 6S, because that's the first time it appears.
6F?
6S.
S.
And then it would be 4F.
So like the end of the electron configuration for zinc would be like 3D10.
3D10.
And then
Perfect.
the next one would be 4P.
Yep. 4P1.
Oh, okay.
Exactly right. So bromine, let's take a look at bromine. 35 electrons. That's going to be a lot of orbitals to label out, and a lot of those orbitals are what? Completely full of electrons. Okay? So what I'm going to do is cheat, and I'm only going to look at that last row to account for bromine. Everything above it, I will simplify out. Okay, what do I mean by simplify out? Everything above it ends with what? What's the last element in everything above bromine? Jump it out a little bit louder.
Argon.
Argon. So I'm going to say, you know what? I'm not drawing out argon's configuration. Argon's configuration, done. What in addition to argon does bromine have? We'd go to the 4s2, 3d10, 4, try that again, p5. So I can use what's known as the noble gas notation. Okay. Why the noble gases? What was one of the characteristics of our noble gases that you theoretically already heard that I didn't talk about? They have all their electrons, yeah. Most stable. They don't react with anything. Why do they not react with anything? There's no place to put an electron. They've completely filled all of their orbitals. Bromine happens to react really quickly. Why? There's one little hole. What happens if I fill that one little hole? It completes it. Not only does it complete it, it becomes symmetric. It is fully filled. That symmetry explains its patterns. Yep. So with all of this, you may be panicking and saying, well, I've never seen this before. And I want to call BS on that, but in just a second. What's your question?
The brackets are necessary.
You should show the brackets. Okay. All we're looking at is labeling where every single electron is located. That's it. Okay. And you again may say, well, I've never done that before. Okay. Do you know where you live? How would you tell somebody where you live? Okay. Country, state, city, okay. Your address, the street. All of those bits of information are exactly what our electron configurations are doing. Except now what we've done is instead of saying the state, we're saying the energy level. Instead of saying the city, we're saying the orbital type. Instead of saying the orbital orientation, we're saying the street. Okay? It's just a way to write down an address. That address is already mapped out. You have the map in front of you, you just have to label it. Kind of makes sense? When are we done? That's good. So our orbital types. These shapes that we just kind of drew out, we've got 3 shapes here. That first one is the S orbital. How do you know that? Because S begins with, fair answer. I didn't actually read that. S begins with, or sphere begins with S. The next one we have the P type, which we know as the dumbbell. And the next one is the D type, weird butterfly thing's not a bad one. It is actually referred to, though, commonly as clover leaf or clover. Okay. What if you called it the weird butterfly shape? Would you be right?
Yes.
This is one of the things that I really dislike about kind of naming things. To agree on a possible combination or a proper nomenclature or discussion with somebody else, you have to use the same terms. Which then means butterfly shape does not work for the d orbitals. It has to get called the clover leaf.
It's almost like you're saying there are these like conventions that people use to communicate.
We have natural conventions within our sentence structures and how we present individual names for our orbital types and everything else. When we looked at the s orbital, what were the possible orientations? 1, because if I rotate it, what happens? I can't tell a difference. P orbital, we end up with 3. Why? Well, it kind of works if we just say x, y, z. So there's 3 axes, so that works. What happens when we get to the d orbital? How many orientations are there? Okay, 5, because obviously if you take a clover leaf and orient that, you've got 5 different ways to orient the clover leaf, right? Okay, you should be confused on that. You can step up and say, yeah, that doesn't make any sense. You're right, it doesn't make any sense because that orientation really only works for the p orbitals. You can tell where my strengths are. I'm in the p orbitals and s orbitals. I don't deal with d orbitals. When do d orbitals show up? With what materials? Metals. Organic chemists deal with non-metals. That's why I don't worry about the d orbitals so much. There are 5 orientations. If you don't know that there are 5 orientations, how can the periodic table help you out with that? How many orientations were there for the s orbital? 1 orientation. How many electrons fit in that? How many columns in the s block? 2. The p orbital had how many orientations? 3. How many electrons fit in each orbital? In each orbital, 2, which gets us a total of 6. How many columns in the p block? 6. How many columns in the d block? 10. If a single orbital can hold 2 electrons, how many orbitals have to be in the d block? 5. That information is buried there. It's not obvious, but it's there. Okay? So, there's our new views. So here's our d orbitals, just for the sake of it. That's your 5 possible orientations for your d orbital.
Front, back, both sides.
Yeah, I was waiting for that one. What about the last one? You're right. The d orbitals don't match the orientation perfectly. We end up getting this weird shape. And everyone goes, why the hell do we get this weird shape? Because physics. Okay? These shapes are the 95% probability of finding the electron at that particular energy level. Okay? Which means if we look within this room, there's a certain probability that you might find me in this front little section. Okay? There's a very low probability you'd find me over there. So if you were asked to draw the shape of me through the course of the room, you might draw this little T shape here. You wouldn't draw me back in the corner. Why not? Not ever there. Okay? When we go through and look at each of these shapes, it's a mathematical manipulation saying, how does that force the probabilities? That's where that last one comes from, which is actually known as the donut. And I don't think I'm making that one up. Pretty sure that's right. I'm pretty sure it's the donut shape. Right? So, capacities. First energy level gets us what sublevel or what orbital type?
1s.
The 1s. Okay, how many sublevels are there?
2. Wait, none.
None. There's only the 1s. There's no sublevels attached with that. How many electrons fit? 2. What happens when I move to the second energy level?
It becomes 2.
Okay. I get an extra type of orbital. So I have the s type and I have the p type. Okay. I have to be more specific. It's not just the s. Which s is it? The 2s. Which p is it? Okay. How many electrons fit in the 2s type? I think I totally read something wrong there. But we'll skip that. The P fits in 6. How many electrons in the energy level? 8. The energy level is in reference to the 2. Anything with a 2 in front of it, you have to total those electrons. That's why we get 8. Okay? That's a lot of memorization. Or, look at your second row, count how many occupied columns there are. There's 8. Okay? So our periodic table has that information there. What happens if we move to the third energy level? What are our sublevels? We have S, P, and D. Those would be 3S, 3P, 3D. How many electrons in the 3S? 2. How many electrons in the 3P? Electrons in the 3D. 10. How many electrons in the third energy level? 18. What comes after F? Why don't we not know? Okay, so we had our orbital types. As we moved up in energy, we had a new type of orbital. So at the first energy, we had S. Second energy, we have the extra one being P. Third energy, our extra one is D. Fourth energy, our extra one is F. Fifth energy, our next one is G. Where's the G block? We could make bad jokes about that.
Is it the second asterisk maybe?
We haven't found it yet. Why not?
We haven't made it or found it yet.
Why have we not made or found it yet?
Because we don't have energy levels that high?
We have 7th. Okay, we can go all the way up to the 7th energy. Why do we not have the 5G?
We don't have enough strong enough energy to make it.
There you're getting at the idea. What happens when we go up in energy? The electron gets further and further from the nucleus, meaning it's no longer attached to it, and it goes into the vacuum. What happens as we move up to, say, element 118? It is now so massive that the last electron for element 118 is effectively in the vacuum, meaning it doesn't exist. It gets a step worse than that, the protons. Okay, what happens when we have a single proton all by itself? I'll give you a hint. It's positive, not a big deal. What happens when we add a second proton? They start to repel. So what do we do to account for that repulsion? We add neutrons. So when we look at helium, what happened to the mass of helium? There were 2 protons, and yet the mass is 4. How does it get to 4 with only 2 protons? 2 neutrons. The neutrons are acting as a glue to prevent the protons from repelling away from each other. What happens when we hit 118? We've put so much freaking glue into our nucleus that the glue no longer holds all of those individual protons near each other. And what does the nucleus start to do? Break down in the form of nuclear radiation. You look at uranium. Why is uranium radioactive? How big it is. Okay. Those elements that are reactive have nuclei that are so large that they physically cannot hold themselves together and they fall apart. That's what we're seeing with our radioactivity. So why do we not see the G? 118 isn't even stable enough to really isolate. Okay? If 118 isn't stable enough to isolate, I'm not going to be able to get up to probably 121 to get to the G orbitals. Okay? Are they there, theoretically? Will we ever be able to place electrons in them? Probably not.
There's also a K orbital, but that one is just so far.
That was just the 5th. So what's the 6th? We have to get an extra orbital. The 7th, we have to get an extra orbital. Okay? Each of those types must stack into it. Okay? Why do we stop labeling them? So we stopped filling them. Okay? If we don't reach them, we kind of ignore them. Okay? So there's all that. Okay? Our electrons are placed in the lowest energy first. They're paired before finding a new home. So we put our first electron into the 1s, the second into the 1s, third into the 2s, because I can't put any more into the 1s. Okay? There's that electron-electron repulsion. Okay? You will see a diagram like this. Okay? I personally find this very confusing, but what we're doing is pretty much creating a grid and then moving through the grid as our fill pattern. That's what our arrow is saying. So we start at 1s, but then we cross-stitch back and we start going to 2s. We cross-stitch back and we go into 2p. 3s, cross-stitch back and we go into 3p. 4s. What happened to the 3d? We aren't there yet. We cross-stitch back our 3d, 4p, 5s. So that little switch that we saw where we skipped the 3d over the 4s, you'll notice it happens again, and it continues to happen as you move into larger and larger elements on the periodic table. Okay? And it's because of that fill pattern. The periodic table gives you a lot of that information. Okay? Yeah. Okay. One of the last big topics I want to get, I say last, that's never true. You're welcome. If we took a look at carbon, our electron configuration, 1s2, 2s2, 2p, 2. If I'm going to want to look at how carbon reacts with another molecule or another atom, I'm going to take that carbon atom and I'm going to bring it what?
Bring it
Closer to another atom. Okay. What's the first thing that those atoms are going to show or interact with? So hint, the nucleus or not the nucleus? Why not the nucleus? Remember, the nucleus is a tiny little spot in the middle. What's more than likely to interact? If I went up to try and interact with you, the first thing that's going to interact are hearts. And I don't mean metaphorically, I mean physically. Are our hearts going to jump out and... No. What's going to interact first? Probably the personal bubble space where you say, stop walking near me, or I'm going to deck you. Okay. Same thing's happening with our elements. We're going to look at the outermost electrons, because those are going to be the ones important. What about the inner? Well, they probably aren't going to do anything, because they're inside, filled, and stable. It's only the outermost that we care about. Outermost, unfortunately, is not a scientific enough term, and we use instead valence electrons. The valence electrons are what determine the reactivity of our individual atoms. Okay? So playing around with those and determining those is helpful. Might be nice if we had an easy way to determine how many valence electrons our element had. Hydrogen has how many electrons? How many valence electrons is it going to have? 1, because it only has 1, right? Lithium. What's its outermost energy level? The 2s orbital with 1 electron in it. So it has 1 valence. Sodium? 1. Potassium? 1. Rubidium? Cesium? Francium? Calcium? 2, because second column. Boron? Why?
Because it's technically the third.
It's kind of weird. It's not quite the third column, right? What's the Roman numeral?
3A.
3. What's the Roman numeral above hydrogen?
1.
Roman numeral above beryllium?
2.
Roman numeral above nitrogen? 5. How many valence electrons does it have?
5.
5. It's on the periodic table. Yes? Okay, I'm letting you process that a little bit differently, but maybe your question will come back. Do you have a question still? Go for it.
It's just like, why helium isn't one piece? I don't understand.
So when we look at our periodic tables, we may wonder about what patterns we used. Okay, so I apologize if anybody's watching this and is getting dizzy, so don't watch the screen. The periodic table that we currently use, we picked the best pattern that we could, or the most ideal pattern in our opinion. Okay, but that does not mean that is the only periodic table. Whoops. What are all these? Periodic tables. A different person went through, found different patterns, and organized it differently. When we look at our periodic table, why is helium shown all the way to the far right? It's a noble gas. Why is it a noble gas? It doesn't react with others. Why does it not react with others? Its valence shell is full. For that first energy level, we have a full valence. Helium is placed over neon because that family isn't reactive. It unfortunately does not pair well with the orbital names and locations. Sometimes you will see helium drawn right next to hydrogen, and you'll see hydrogen shown right next to helium for that very same reason. Hydrogen has the reactivity of both the first column and the 7th column. Okay, so you'll see it in both places. Same deal for helium. That is it by far, so if you've got questions, by all